After the more philosophical and general overview on uncertainty quantification and Bayesian evidential learning, we'll start now with the really technical material. Falsification of prior uncertainty is probably one of the most important steps you'll ever do in an uncertainty quantification. It's essentially trying to recognize whether your prior uncertainty model is not falsified, means it's not proven wrong, and therefore you can proceed with the Bayesian methodology. There's some reading to be done there. Chapter 3 has some sections on dimension reduction, which we'll use extensively in the falsification. There's also a recently published paper, uncertainty quantification of medium-term heat storage from short-term geophysical experiments. So there we use the Bayesian evidential learning method, and we go through the various steps, including the falsification step. So let's come back to this design. I think it's very important to follow this protocol and to follow this particular design and not deviate from the design. Otherwise, we'll run into problems and confusion later on. If we're doing an uncertainty quantification, particularly one that's model-based, so later in the course, we also talk about data-driven uncertainty quantification, and then the design will be somewhat different. If it's a model-driven uncertainty quantification, then always we start with the design of the model and the prior distribution. And so the question now is, what's the relationship between this prior distribution and the actual observed data? Can we use the prior observation, prior distribution, do Monte Carlo, forward simulate the data variables, and then we have a statistical representation of the data variables, and we need to compare it with the observations. So in that falsification step, we're not trying to match observations. We're just asking the question, can our model predict the observation? It's a very fundamentally different question. So let's talk about the particular example that we'll talk about. It's also mentioned in chapter 1 and chapter 8 of the book. We're looking at low enthalpy geothermal systems where we use the groundwater as a heat exchanger for heating and cooling. So in the summer, you would like to use cooling, and in the winter, you'd like to use heating. So or vice versa here. So the way it works is that you will, in the winter, recover the warm water that was injected in the summer, and so on. So the question is simply, how do we design such systems? And in particular, we're interested in what is the kind of heat pump that we like to use. If the system is very efficient, then our heat pump doesn't have to do a lot of work, and so we'll use a less powerful heat pump. Otherwise, our heat pump will do a lot of work, and so we need to design a different heat pump. We need to get a different heat pump. And so the question is, how can we decide on the right heat pump? So this is a decision question. That's, of course, subject to a lot of uncertainties. So if a given site, shall we go ahead? And if so, what would that be based on? And often it's based on the fact that there's a risk of when we recover the hot water, for example, that will be a very quick temperature delta T drop over time, and that's not efficient. And so we'd like our delta T to remain long for a very long period of time. So we can't assess that because these periods of times are months. And so we'd like to do just a shorter term experiment where we can verify or investigate whether for this site this system is viable. The information source that we'll be looking at is what's called time-lapse electrical resistivity tomography. And so we'll talk about that a bit. So in time-lapse electrical resistivity tomography, essentially what we're doing here is using the change in heat as a function of temperature to measure essentially what the temperature distribution is in the subsurface. We do a time-lapse survey in the sense that the time-lapse survey is where we design a baseline of the heat, and then we look at the difference in heat as we make that heat injection. The nice thing about doing the baseline is that we can already we're not worried about any non-important differences that could also impact resistivity surfaces such as the lithology, etc. So this is the setup of the experiment. We do a heat injection. So here we do a short-term heat injection, and then we do over short-term, we measure that geophysical self-potential profile at a certain location. It allows us to get this electrical resistivity tomography. So the problem, of course, is it doesn't look as nice as it does in reality. In reality, you have all kind of heterogeneity that may make this picture look very different. So this is typically, say, a setup of the of such an experiment where you have an injection well and a pumping well, and so you inject hot water Here we have our ERT panel that's about 8 meters away from the injection well. And there we can measure our electrical resistivity, do inversion, and see what we get compared to some baseline. In this particular case, they also made boreholes where they measured temperature using essentially fiber optics. And so that allows us to then get some idea of again, use that information as falsification in the modeling problem. If you would just do deterministic inversion, then you would get something like this. So you would see a change in temperature as we do the experiment. And so already we notice that we see some kind of a change in, we don't get that nice big plume that we saw before, but we get 2 plumes. And so that probably has to do with heterogeneity. So you say, yeah, well, that seems like it gives an answer. That's true. It gives an answer to the temperature distribution of the subsurface. It doesn't give an answer to the heat pump question. And so that will require forward modeling of the long-term experiment, which is forward simulation of what would happen if we actually do the injection over longer, or the production of this heat over a longer term. So deterministic inversion, which we'll cover later, is useful, but does not provide a uncertainty quantification on what we actually like to know. So we have to, as I mentioned in previous slides, is that you have to start with a statement of prior uncertainty. So basically a statement of what we don't know. And we don't know a lot here. This is not like some kind of a oil reservoir or groundwater system that's being managed. It's basically, we like to know whether or not we should do this kind of low enthalpy system. So we only have a few boreholes. We know probably a little bit about the subsurface by drilling in those boreholes. The vertical variability is something that we will see. We can measure some electrical properties of along the boreholes with simple borehole tools, and possibly we can estimate the gradient. And the gradient is not expected to be changing a lot, simply because we are looking at a very small area of the subsurface, 20 meters or so. So what is then done is make some initial statement of prior uncertainty. This is not the prior uncertainty. This is some initial statement and hypothesis that needs to be tested. So as you notice in this table, and I recommend always start with these tables and to be very precise in the tables of what is exactly uncertain and what's being generated. So we notice that there are a number of parameters that are determined to be fixed and certain. So this is a particular modeling choice that may not be correct, of course. And we also have some statement around uncertainty of hydraulic conductivity and its spatial variation, as well as porosity, as well as the gradient that is available. So we go from 0 gradient, having no gradient, to having a small gradient. And so this is an initial statement of that uncertainty. So what we do next is then Monte Carlo. So in this part of the exercise, we'll just focus on this mostly on this top bit because we're going to do falsification. So we'll take our previous table, we generate many fields of hydraulic conductivity, many gradients, porosity, we run a simulator, and we do some geostatistical simulation, and we create many subsurface models. Once we have these subsurface models, we can now apply our forward model for the data, so that models essentially or simulates the particular data observations we have, and that's something I'll cover in the next slide. So again, this has to be only relative to the specific observations we have. So this is not just a general forward simulator, it's something that simulates the observations. So resulting from that, we get a Monte Carlo answer of the observation. So now I've noticed that I've changed the italic font into the bold font, indicating that we have a vector here. So this is high dimensional, this is high dimensional, and these distributions are being used to generate that variability of these high dimensional variables. So here's what that means for this particular setup on the low enthalpy problem. So as I mentioned before, we first start with simulating model realizations. So these are models of hydraulic conductivity, flow gradient, etc. So from that, we can predict the future, which is what we like, which is the prediction variable, which is the long term. So this time is long term, and what we'd like to have is the delta T, the decrease in temperature as we're producing the system. So for each model realization, I'll get that. Then secondly, of course, I'd like to also get a simulated data variable. So in this case, what we'd like to get is the change in resistivity as function of time, because but this is also short term. So the question, of course, that we'll address later in the course is how can this be used to predict this? This is some different variable, it's longer term. This is another variable, shorter term. So the way that's done is that by flow simulation and heat tracing gives you simulated heat in the entire model. Then based on petrophysical relationships and geophysical forward modeling, we then get what that would mean in terms of a resistivity change at a particular electrodes. Remember, I have a drill in the subsurface. I have many electrodes where I measure essentially that delta R, and this is just one electrode. So how does falsification work? So this is really now an important slide, and the next one as well. So the hypothesis is that our prior model can predict the observation. So what does that really mean? It means that if we take our prior model and we have uncertainty on the prior model, and we have a given forward model, and we have also uncertainty on the data variable. So the hypothesis is that the data variable, and when evaluated in the observations, is not zero. If that would be the case, then our prior model would never be able to predict that. The problem, of course, in reality is that that this f of d, because d is high dimensional, is also it's an unknown multivariate distribution, certainly in the Gaussian distribution. And we have only samples, Monte Carlo samples, to estimate it. So the best we can get is not f of d, but an estimate of f of d. And then, of course, the other problem is that to do this estimation is very difficult because we're dealing here with d possibly being very high dimensional. In our case, this particular geothermal case, it's a series of changes in resistivity over time at various electrodes that we do the measurement. So how do we do that? Well, solution to 2 is the high dimensional is to reduce dimension. So we're going to take our d and make it simpler and make it lower dimensional. So we'd like our dimension of this d star, which is our lower dimensional variable, is just obtained through a mapping from d into d star, that the dimension of this d star is less than d. So why is this possible? Well, the reason this is possible is that we have essentially the curve that we're generating is a curve. So there is a systematic variation. It's not that what we're getting in the d is just a random variation. Is we get a systematic variation. It means that in a systematic variation, there has to be dependency. And so that is created essentially when you go from the model world into the data world. So how can we discover that dependency? Well, there we have to do apply statistical methods. And there are many methods available. I always suggest to start with PCA, principal component analysis. It's the simplest method around. It's very popular these days. Also, are neural networks or deep learning networks. Those are fine, but they may be difficult to apply. So why can we do the statistical method? Well, we have done Monte Carlo. So if you've done Monte Carlo, then what's available to us is that we have this multiple realizations of the data variable. So we can run principal component analysis, and we can start to reduce dimension by finding out through principal component analysis. It will basically be a matrix multiplication, what this transformation is. And so you go from then Monte Carlo samples after doing PCA to Monte Carlo samples now of much lower dimensions. That means that we can apply also equally, we can plug in here that d ops, and that gives us down the d star ops. And also, what we also really nice often about the methods of principal components is that now we are in an orthogonal world. So we have orthogonal axes, and calculations, in particularly probabilistic calculations, become much more feasible in such axis system. So once we have that, we can now estimate the d star, the f of d star, and then evaluate that. And so the idea is that if d star is a good approximation of t, and the estimation is with large confidence, then this is a hypothesis that we can then evaluate whether or not this is zero. So in what comes next, you notice that in this method of falsification, I do not specify necessarily what is the specific GH, what are the specific f of m, or what are the specific methods of statistical evaluation. So this is a broad framework that can be applied into many situations, not just say this low enthalpy subsurface and whatever. This can be applied to any data modeling environment where we are looking to apply Bayesian methods. So let's now go back to our geothermal example. So here we see we have that, put a pointer on, we have that short-term experiment, only 120 hours, where we see a change in resistivity in various electrodes. So what we have here, all these black curves, is the Monte Carlo result for the observations, the data variable, and then we have the red, which is the observations. So it's always encouraging that we see that the red is somewhere captures, probably except here, is somewhere captured by the Monte Carlo results. So if we do principal component analysis, basically what we can do is we get principal component scores. So we can look at these principal component scores individually. We get principal component scores, so the first principal component score for the D star, and also of course for the observation. So a necessary condition is of course that, a necessary condition is of course that this red dot has to be within the black dot. That's a necessary condition. It's not a sufficient condition because we also need to look at the high dimensional space that's being created, and that's what we observe here. So here we're looking at these first three components, 1, 2, 3, which captures about, let's see, 11, 11, 10, 92, 3% of variance. And we notice that our dot is within, again, within this cloud of points. Similar here, this is for, so this is just another example of the same. So the more testing, the better. Remember that we also had temperature measurements or temperature decrease measurements in those boreholes where we had fiber optics. And so there we get also forward predictions. And so, so we notice here that, again, our red curve lies within this, this gray set of lines. It's a little bit dangerous to just look at the red curve versus the gray curve. You say that looks good. It's also important to look at higher dimensions. For example, there's another example that we have in the book, which is not to do with the geothermal case, but an oil reservoir case. So here we have production data in a reservoir and the forward simulated production data. And so it looks very encouraging that we indeed have large similarities, at least in terms of the behavior. But actually, if you do principal component analysis, you find here that your observation lies far outside the cloud of points. So by using anomaly detection here, using SVM methods, we can actually detect that. The reason for that is that the shape of this curve is very different from the shape of the forward simulated model. So it's not just a matter of objective function, right? An objective function would measure something like that, but you also need to worry about the shape of the curve to that. So we'll return to that issue in chapter 7 and later in the course. Okay, so now what we'll do is we've given an overview of what is the falsification principle and in general methodology. So now we need to look a little bit at specific tools of dimension reduction. And I'd like to refer to the book where we use this notation. I think this notation, it's important to look at that. A couple of points I want to point out is that in the book we'll use always L as the number of samples and N as the dimension of the samples. And it will allow us to track that because this L and this N and their relationship are very important in the course. Okay, so let's start in setting up the formulation of the problem. So here we have a definition of the model as we've seen we need to do. We do that in Monte Carlo, we generate many model realizations. So that will be the indicator, the runner L, which is small l, which runs to 1 to big L. So then we take all these models, we evaluate the forward data model, and we get many realizations of samples of D. So we can put all that in a matrix, and so in a matrix is of size n times L. Same with the data matrix is of size nd, which would the data dimension times L, because of the same amount of realizations. What's very important, we have discussed this before, is that in most uncertainty quantification subsurface, we'll never generate more realization than the dimension of the realizations. And this is simply to do with the fact that what is needed is essentially evaluation of the uncertainty on prediction variables. We're not so much bothered too much, at least with uncertainty in the model variables. It's important, but in the end, we have to focus on uncertainty and in the prediction variables. And so the prediction variables often are much simpler. They are volumes or recovery factors, or where should we drill a well, or how should we design that well, etc. So that's very important to keep in mind and has some consequences in the choice of the dimension reduction methods that we'll be using. So let's start with some basic algebra. So the multiplication of vectors with matrices and the changing of coordinate systems, I think that is very important. So for example, here, our forward model could simply be a matrix. And if the the ranks are the same, then we are doing a linear projection that essentially is unique, and so we will have a unique solution. However, the matrix becomes of lower dimension, then we have multiple solutions possible, and we call that sometimes, in some fields, call that the null space. So what such projection does is it takes, if I take a cloud like this, which is just random, it turns that cloud into a different cloud which is a different shape. And so what we like to discover is what's the shape of this new cloud, how can we explain that, and how can we model the variation of the shape on this cloud. So to do that, we need to do singular value decomposition. So whether you use square or non-square matrices, you can always do this decomposition as follows. You get a diagonal matrix, you get a vector of eigenvectors, matrix of eigenvalues, matrix of eigenvectors that are unitary. So it means that V transpose V is identity matrix. So this can always be done. The relationship between square and non-square matrices and singular value decomposition, eigenvalue decomposition is very well known. So what does that really mean? And I think it's important to understand that, what the exact meaning is. And always the way I think about it is that eigenvectors are something that quantify shape, and eigenvalues are things that quantify variation. The other thing that's really important about eigenvalue and singular value decomposition is that it allows us always to work in orthogonal coordinates. Because as you know from the previous slide, if you've seen from the previous slide, is that if you take, say, a square shape in the space that we have, say the vector x here, which is some vector here, another x vector there, where if you then multiply that with a, you get into this new shape, y is a times x, so you get a y vector, and the shape is now skewed. So what essentially eigenvalue and singular value decomposition say is that you can actually work in two spaces that are still orthogonal. So if you take the U matrix, multiply that, you get something which is a rotation. And once you apply that, you apply squeezing to that situation, you get this. So we have a rotation and a squeezing. So the squeezing is essentially variance, right? So here the sides are still equal. And so variation now is seen that there's more variation in this direction than in this direction due to this squeezing. And then we project everything back using the matrix V. Important to remember is that eigenvectors quantify shapes and eigenvalues quantify variance. So we can also have two views of the same data matrix. So remember that in previous case, I had here the model and the data, but you now can see that you can put anything in here. So it could also be the prediction. So in general, what I have is I have something of dimension n, a large n, so n large in our case, which is the size of the problem. And I have something of dimension L, which is the amount of data that we have about that. So the amount of data does not refer to physical data and whatever, it refers to the amount of samples that are available of that high dimensional data vector. So there's two ways then to proceed to view this matrix, row-wise and column-wise. So one way is to view it in Rn. So here the axes are now go from x1, x2 till xn. So this is very high dimensional space, and we have only L samples. So this is the model space where we have very few samples. Here we look at the sample space and we embed the models. So this is the dimension of the model. So we have n models. So for example, you have one property of the model we look at, and we look at the various realization of that one property of the model. So we have essentially n points. So in our application, this space is very empty and this space is less empty. And so that becomes an important factor later on when we look at dimension reduction. High dimensions are really difficult to understand. We can look in 2D and 3D, but once you get much higher, you can imagine 4D is space-time, but once you get much higher, it's sort of hard to understand. One thing we have to understand about high dimensions is that they become empty very quickly. It's very lonely space when you go to high dimension. And to see this, we can look at a very simple experiment that's often shown to illustrate that, which is this idea of embedding a circle into a square. So if I look now at the empty space here, which is the space here, we see that that covers only 21% of the total space. So this is 78%. This is going to go down, obviously, if I embed a circle into a sphere, into a cube. The circle is only 52%, so on. So now I can start calculating this in higher dimensions with hyperspheres and hypercubes, and you see that after 8, 9, 10 dimensions, we basically get empty space. It's almost nothing there. So that has a problem that we need essentially increasingly exponentially more samples in order to fill that space. So explicitly, the space becomes very empty very quickly. However, that's just the explicit dimension. The implicit dimension of the space may be much lower. In other words, if you have strong correlation between variables of samples, that means that there's something that is a much lower dimension than the actually explicit dimension of the space. The fact that our implicit dimension is much smaller than our explicit dimension due to the correlation of the various variables in play here allows us to do dimension reduction. So there are two ways of doing this dimension reduction because we have two ways of representing the data space. So let's first consider the Cartesian space of size L, the sample size space. So here, what I'd like to do is look in my dimension RL. So we have here the various samples of the various properties that we're studying. We'd like to represent all this information. So we have various samples here. So there's a particular sample, there's another sample, another sample. We'd like to essentially represent all this information. Let's start just with one dimension. That means what we'd like to do is find this line here, this vector, such that if I project onto this vector and reduce all the information to just one-dimensional representation, that I lose a minimal amount of information in doing so. So this is the projection, right? So I take some kind of data point xn here, sample point, sorry, xl, multiplied with that particular direction. What I'd like to do is that this projection minimizes the least square difference between the two. So with my least square difference is my definition of the loss of information. So we can work this out and show, and this is done in the book, that this is equivalent to maximizing this form here. So now we see that in this form, we see this matrix X transpose X appearing. So this matrix X transpose X is of size n times n. So n, capital N times capital N, which is the dimension of the vector X here. So this is equivalent, of course, to the first eigenvector of this particular matrix associated with the first eigenvalue. So, and then you can see if we take a second one that's orthogonal to the first one. And you notice that I can only take in this three-dimensional graph, I would take only 3. So in an actual dimensional, the maximum size of that would be L. But if I take a second one, then that's orthogonal, then I can ask the same question: is what maximizes that second one subjected to the first one that's already obtained. So now what we'll do is take the same exercise in the previous slide of dimension reduction, but now apply it in the Cartesian space of size n. That can be simply achieved by replacing the matrix X by the matrix X transpose. So then I get the same maximization problem, and so instead of the matrix X transpose X, I end up with the matrix X transpose. So now I have different eigenvectors and different eigenvalues. Notice that the rank of these matrices are exactly the same and equal to the rank of the matrix X. So the question now is, what is the relationship between the V and the U and the lambda and the mu? There has to be a relationship because essentially we have not changed the information itself, we just worked in different spaces. So there has to be a relationship between the eigenvalues and eigenvectors into these two different spaces. So that relationship is written here and can be easily derived. So we notice that, first of all, which is interesting, is that eigenvalues are exactly the same. And there's a relationship between eigenvectors of respective matrix eigenvectors. So in reality, then you have to make a choice where to work. And most of that will depend on the size of this matrix. The size of this matrix is L times L. So in our application, it's small. The size of this matrix is N times N. So in our application, this is large. Okay, that's just pure algebra. So what if the x's that we have obtained are actually samples from some distribution? So that means our x's are now obtained by Monte Carlo drawing, for example. So these are our samples, outcomes, or realizations that we have drawn. For example, it could be model realizations, data realizations, and prediction realizations. So what the way we'll proceed is exactly the same. So and now we call this projection, we call it a standardized linear combination. So we take the elements of this vector and we start to make linear combinations of them. And then we'll see by doing these standardized linear combinations that we get new vectors or new data points that have interesting properties. And that will be the dimension reduction representation of this X where the components of those X are now orthogonal. So the same algebraic problem that we had before with least square minimization that led to dimension reduction can be now cast within the probabilistic framework. So instead of now doing a least square minimization, or that maximization that we ended up with, we'll now do a maximization of that variance. So we'd like to maintain the same variance, or at least as high as possible when we do that production. Maximum variance would mean minimum loss of information. So we keep them high variation as possible. So if you work that out, then you end up again with some similar expression. Now instead of that matrix X transpose, remember we had this matrix X transpose X here, we get now the variance of a vector. And so the variance of a vector is nothing more than the covariance of a vector. And so that covariance, of course, the way that will be calculated is exactly this way. It's using the X transpose X, and that's what we'll see in the next slides. So essentially, the statistical representation of that least square minimization is a maximizing of variance, and it's called principal component analysis. So this is then the probabilistic result of the same problem. So what I'd like to do is to obtain a vector y whose components are uncorrelated. So this vector y, I'd like to have a vector whose components are uncorrelated, and the way I do that is by a projection of the original vector x using the eigenvectors into that vector y. We can then show that the expected value of y is 0, because of course I subtracted the mean here, that the covariance of any components of y is 0, so they're uncorrelated, so these are orthogonal, that the variance of each one of them is the eigen value. So again, we see here now what we mentioned before is that eigenvectors provide shapes and eigenvalues provide variance. So here we make really nicely that connection. So when you're thinking all of these complicated math, or if you find this complicated math, again, what I'd like you to take away here is that these vectors look what is the various shapes in the space of X, and the lambdas look then along those directions what's the variance. So principal component analysis then work practically as follows, is that first I calculate the average of my samples. I center those so I can calculate a centered covariance. So this is the estimated covariance matrix. I decompose that covariance matrix using eigenvalue decomposition, and then I can project the values, the samples into possibly a lower dimensional space, in the sense that we'll take less of the n and thereby still maintaining lots of variance. So let's do an example. So here I have generated many of these images. And so we notice in these images that there is some degree of spatial correlation. So it means that the red are somewhat connected and the blues are connected to each other. So I've generated several hundreds of those, and so that's a lot of information to carry around. And so the question is, can we reduce this information without release essentially the storage, let's say, without losing too much information? So you can see that this is basically an image can be put into a vector. And so each vector it's a high dimensional model here, which is 100 times 125. So that's 12,500 essentially samples that I have per each of those vector. So my model consists of dimension 12,500. And so then I have a few hundred of those, so the number of realization L is then much less than the dimension of the model. So what I do is I put as all calculate the covariance matrix, just take X transpose X basically, and divide by L, and I can then do principal component analysis. So in principal component analysis, we obtain two things. We obtain the eigenvectors that quantify shape and the eigenvalues that quantify variance. So what's often important in principal component analysis is to plot these cumulative explained variance. So for example, here we notice that the first principal component explains a little variance, and if we add to that more principal components, then we get more and more variance. So you notice that at some point around, say, 95, you use 30 of these principal components can represent 95% of the total variance. So here we see the principal component scores. We'll talk about that a little bit in the next slide as well. So these are the y values. This is y1 and this is y2. So here we see the principal component vectors. So our data, essentially, that input data was an image. So that also means that the eigenvectors are also images. And so we need to see some interesting features appearing in those images. We see, for example, that the first principal component seems to be some kind of average of the image. The second principal vector seems to be indicating some kind of a gradient in the image. So it looks at high, low. And so the third principal component looks at another type of gradient, but now in another direction. The fourth principal component vector seems like to be a curvature. So we're trying to measure curvature here by that. So what does it mean, gradient, vector, etc., curvature? It essentially means that if I take an image, then I can write that image as linear combinations of these basic images. It also means that each of these is measuring a different element of the image, a different shape that occurs in the image. And the way that is done is by using this as a filter. And this filter, or this principal component vector as a filter, provides me with a principal component score. So of course here I've only the first two dimensions, but you can imagine having any number of dimensions. One neat element about principal component analysis is that you can reconstruct from lower dimensions back to higher dimensions. Recall that the principal component analysis is a method that try to achieve this lower dimensional representation of an original high dimensional object. So here we see that, and that basically works through this reconstruction. So previously we had u transpose times x. So the way we then is to essentially revert it and use now the y transpose times u as a way to reconstruct. So if I use all of the y's, remember the y's is of dimension n. So I have as many principal components scores as I have the original dimension of the vector. And so if I use all the principal component scores, then in other words, I use this equation where our n is n to n prime runs to, where n prime is equal to big N, then I get a perfect reconstruction. Now we can see that I can start chopping off this series. I can say I'm not summing over all big N, but I stop at some particular point. So for example, here n prime is 15. And so now I can try to reconstruct this original image using only 15 eigenvectors instead of all the eigenvectors. And what you notice is that we get a pretty good result. It's approximative, but still, with only 15 principal components, I can reduce dimensions significantly. This is not always the case. If your original image is highly varying, and it's logical that you need more principal components in order to make that reconstruction. So for that reason, because we can go from high dimensional to low dimensional, and then uniquely back from low dimensional to high dimensional, we call PCA a bijective operation. So principal component analysis can be applied to any kind of object as long as that object can be put into a vector. For example, here we see some curves. It's actually a concentration of a contaminant. A whole bunch of curves. And so the question is, can we do principal components on that? What would that mean? So if you look at these curves, then we always see that these curves are very highly correlated, right? So they all seem to start at 0, and at some point they start to increase, and at some point then they start to level off. So it seems like very few principal component scores will be able to represent this entire system. And that's what we observe here on the right. So here on the right, we notice that if we look at 2 dimensions, we get 99% of variance. And then at 3 dimensions, we pretty much get all the variance. Here we see again the y vector. So the y vector, where you get 96% of variance in the first component of y, and the second component of y, you get 4%. So because we have curves, instead of now eigenvectors being images, our eigenvectors will be curves. And so the first eigenvector is simply the average. Second eigenvector seems, again, like in the previous case, so whereas the second one is the green one here, seems to be indicating a gradient of some sort. And again, we can do reconstruction, which happens essentially we can perfectly reconstruct this using only two principal components. Sorry, I think it's here 3 principal components you need. Okay, so if PCA works on X transpose X, what about working with X transpose? We can again do this exact same thing. Now, of course, we get a matrix of size L times L. So the dual of principal component analysis is called multidimensional scaling. And so we'll discuss that a little bit. To introduce multidimensional scaling, let's introduce this very simple problem. Imagine you have 9 cities in the United States, and what is given to you is a distance map between these cities. So of course, the distance between Boston and Boston is 0. The distance between Boston and New York City is very small. But the distance between Boston and San Francisco is very large. The question we are asking ourselves is, using this distance information only, can we map these cities onto a map such that the distance between the cities in this map is preserved as much as possible? In other words, what I'd like to do is create a map such that the distance between Boston and New York City is 206 miles, and the distance between San Francisco and Boston is 3,000 something miles. So that is the map here, and the way the operation of doing that is called multidimensional scaling. So you notice that this operation works on the sample size here, right? So the sample size is the amount of cities that are available to you. So we notice something else weird in this plot is that everything is upside down. And so what we notice, of course, is that this projection is not unique. If you're given distances, then I can rotate the image, I can flip the image, I can reflect the image, I will still get the exact same distances. So to understand multidimensional scaling a bit more in theory, we'll first introduce a relationship between Euclidean distance and dot product. So in the previous slide, I was interested in the distances between objects, which is different from principal component analysis, where I was interested in the correlation between objects. So what is Euclidean distance between objects? Well, Euclidean distance is simply defined as this very known equation. What's also very interesting, if you work this out, then you write this Euclidean distance as the dot product of this one, the dot product of this one, and the cross dot product of this one. So of course these project on themselves, so these are now called dot products, and this is another dot product. So that is basically the definition of dot product. So now you notice that I can build a relationship between the dot product of L transpose and the Euclidean distance of L transpose. The only thing I need to worry about is to center that dot product property using these B values. So the way we then represent that information is then in a matrix. We say, let's put all these, you notice if I move this minus 2 to the other side, I get 1 is minus a half of this Euclidean distance. I put this in the matrix A, and then if I take the centering matrix H, which allows me to account for this here, if I multiply H times A and H times A, what I can back then is X transpose, which is our dot product matrix. So we notice now that what we've done is made a relationship between Euclidean distance and dot product, and that the dot product matrix is actually the matrix that I'm interested in. Previously in principal component analysis, I was interested in X transpose X. In multidimensional scaling, I'm interested in this matrix X transpose. So if I take then the eigenvalue decomposition of this matrix B, so now that's the eigenvalue decomposition of the matrix X transpose, I get this eigenvalue decomposition. And so now what I'm going to do is to split this up into 2 parts. Into this part, where I take the square root of this diagonal matrix, square root of this diagonal matrix, and I have now this matrix. So because B is also equal to X transpose, I could say, I could equate this part to X, and I equate this part to X transpose. So this is now the definition of the projection. So it's no longer unique because there are many ways of doing this. You don't have to take this equal to X or X transpose. There's many ways of creating this. And so what we'll see in a bit is that multidimensional scaling is not bijective, and so the reconstruction or the unique reconstruction is no longer possible. And that's what we saw in the slide when we talked about the fact that once we have the multidimensional scaling result of the cities, we can flip and rotate and reflect things around. Okay, so let's leave the math behind and let's talk about an example. So here an example where we have given basically overhead shots of a Flume experiment. So a Flume experiment is a simple experiment, or not a simple experiment, it's an experiment that is done in a laboratory in a tank model where basically this is about 5 meters, say, by 3 meters, where we try to recreate, for example, in this case, a deltaic depositional system. And so we can record and take photos of that, and we can look at which areas are flow and which areas are not flow. So now I have essentially a number of samples. In this case, actually I have 136 samples. And the question is, just like before, would I be able to do principal component analysis to reduce dimension? The problem with principal component analysis, it doesn't really work very well for binary information. And this is why. So here we see the first 6 principal components that we have. And so we no longer get that really nice sort of gradient and curvature information. It gets much more complicated. And because our variable is binary variable, the only way to perfectly reconstruct it is use all principal components. You notice that if I use less and less, if I use only few principal components, even up to 50, my image starts really to look like my original image, but I don't quite get to this binary case. So you could say, well, I could take a truncation, and that's all true, but even that truncation will lead to truncation means a threshold, and say classify all the yellow as channel and all the blue as non-channel. I will still not get a perfect or a good reconstruction of this original image. So what about then the multidimensional scaling? So multidimensional scaling, we noticed that we use the Euclidean distance, but one of the really appealing properties of multidimensional scaling is that you can use any distance. For example, you can use the modified Hausdorff distance, because if I'd like to measure the distance between the various images in my Flume experiment, really what I'm looking for is how different in shape these particular images are. You see that the channel morphology and distribution is changing in time, and so the shapes are changing in time. This Hausdorff distance is used a lot for shape detection, and so it's a very simple idea. Suppose you have 2 objects and you would like to know how far they are apart. So one thing, of course, you could take is the center of this object and the center of the other object and measure that difference, but you can understand that that's not a good measure of difference if the shape of the object is very complicated. So the way it is done in the modified Hausdorff systems is that first we're going to look at, say, this object. We're looking at a point here, and we're looking at, for this point, what on all the other points here on that surface is closest. And of course, this point is closest to that point. It's further from that, so that would be this particular distance. And so now what I do is I do that for all of these points on this surface, and I create this sum. The problem with the sum is that it's essentially it's asymmetrical, right? So I started with this image and I calculate distance to that image. That's not good for a distance. The distance you'd like to be symmetric. So the distance between object A is the same as the distance between A and B is the same as between B and A. So what we'll do is we do exactly the same thing for object B. We take object B and we measure the distance to object A in the same sense. We take a point. We look for the point over here of all this point set, which is the closest, and I get this distance. So then I take the maximum of those 2 distances. So I have this distance, that distance, take the maximum of those 2, and then, of course, you get symmetry. The maximum of A and B is the same as the maximum of B and A. So that is the modified Hausdorff distance. So why is this better than Euclidean? Well, what does Euclidean do? Euclidean just looks at the average square difference of pixels, and it's not a good measure of shape, evidently. Here we see this particular shape, and this particular shape is 7. It's clearly that these are very close, and it's much closer than say this 4. But Euclidean distance just looks at the amount of overlap. So what we do in Hausdorff distance is we take essentially we take the edge, we use the edge detection, we find the edges, and we calculate the distance between these point sets. And so then we notice that the modified Hausdorff distance indeed shows that this is much smaller. So here's an example where we take those images and we create multidimensional scaling. So this is exactly the same thing that we had before, remember, when we had cities. So now we don't have cities, but we have images. And so what we do is we project those images into space, and we get this really nice clustering of images. So images that are close by, for example, this image 101 and that image here, they look very similar. Images that are far apart, for example, this image with that image are very different in shape. So with Euclidean distance, you would not get this nice discrimination. So, okay, what have we got now? So we've done principal component analysis that works on X transpose X, and we've done multidimensional scaling, which essentially works on X transpose. So in summary, we could say it as follows then, that X's are any matrix that contain L realizations with vectors of dimension n. We can work in Rn, dimension n, where we have covariances and we do principal component analysis. So here dimension reduction is achieved by taking less principal components. So PCA is bijective and unique reconstruction is possible. In multidimensional scaling, we work in a different space and we work with the dot product X transpose. One of the interesting ideas that you can do in the previous slide is saying, how can we do dimension reduction? Well, I had 136 images, but it was also clear that these images are images similar to each other. So one way of doing dimensional reduction is by taking less images out of the sample size of 136. In fact, if you look at the book, we show in the book that you only need about 6 to 7 images out of the 136 to represent reasonably well the spatial variation that we saw in those Flume experiment images. The only downside of MDS, because it's distance-based and not correlation-based, is that there's no unique construction. Obviously, if I only have 6 images, I cannot purely have those 6 images. I cannot reconstruct perfectly the remainder 136 images.